Last talk of our afternoon session. It's my pleasure to introduce Jan Rellemeyer from Delft. Also, really my pleasure because I know Jan from way back when in, I guess, early, I can't remember exact time, 2006-07 time frame. He was one of the second invited researcher of the OSGi Alliance back when I was participating in OSGi more, and I've watched Jan's career since, and it's been a pleasure to see, and we'll hear what he's been up to recently. So Jan.
Well, thank you very much then. So today what I want to talk about is the benefits of modularity, and we're working towards an empirical study of the impact of OSGi on software quality. Quick disclaimer, we're still at the beginning, so this is work in progress. Don't expect groundbreaking results yet, but we are trying to lay a solid foundation and also rely heavily on student labor. So, you know, that will take a little while until I have capable master students who can really drive this forward. Yeah, so let's just briefly talk about what my relationship with OSGi is. You already heard I've been working for a long time with and around OSGi. Starting back from my time when I was at ETH, so I did my entire PhD around the question of modularity and how it impacts system design. I did Concierge, which was a small footprint implementation of the OSGi core standard, now an Eclipse project. And I did ROSGi, which was kind of the first ancestor of distributed efforts to do OSGi in general. And that recently got the 10-year best, what is it called? 10-year test of time award at the Middleware conference. So it has become somewhat influential to the scene. After I graduated, I moved on to IBM research. I continued to work on OSGi, and I especially was involved in the REST management service. And now I am at TU Delft, where my focus has shifted a little bit, so I now work on large-scale data processing and distributed machine learning, but I'm still very interested to see where OSGi is going, and I would like to contribute a little bit to the understanding of the impact of OSGi through this study. So, if we just talk about software quality metrics in general, right? How many of you in your organizations are using software quality metrics of any form or shape within your processes? So quite a few of you do, right? We will see if this is the same thing that, you know, the scientific side considers, because a lot of those metrics are actually very holistic, and they cover the entire cycle of software development, starting from, you know, the process, the project, and all the way to the product. I would say this is more the management view, right? There's absolutely nothing wrong with it, and there are there's interesting literature on each of those points, but what we are looking into is something that is a little bit more empirically measurable, right? So in software engineering as a computer science discipline, what we often look into is code quality metrics, right? So the truth is in the code. That's the idea. You look into the code that people write, and then we try to infer, based on specific properties, what is, for instance, the efficiency of the code? And now by efficiency, I don't mean runtime efficiency, but more is the code efficiently expressing the functionality, right? Is it an efficient implementation in terms of that? What is the complexity? And complexity has many negative, negative consequences on the long-term maintainability of code. What is the understandability, right? Code is rarely a one-person effort, so people have to, you know, be put on a project. Can they jump right in and understand what has been written so far, or is it, you know, very difficult for them to understand? Is there a chance of reusability, right? Can the same code artifact be used in a different product? And in the end, what is the testability and therefore the long-term maintainability, right? Can we assess the code as to correctness regarding certain expected functionality, and can we evolve the code over a longer time and keep it alive? So the traditional metrics, the one that maybe all of you know is McCabe's Cyclomatic Complexity. This is one of the very popular metrics, and it's still probably widely used because almost every tool that provides software metrics supports it, right? It actually has a pretty profound, root in theoretical considerations, in the sense that it tries to express the idea of how many linearly independent paths do there exist through code. And this is essentially a function of how many branches and nested control flow instructions you have in your code, right? So the general formula for calculating that, one of them, I must say, because there are many alternative formulations that all lead to roughly the same results, is that you take the number of edges minus the number of nodes, and then you add 2 times the number of connected components. So that's something out of graph theory, right? And if you do that, then you can assess what is the complexity of your control flow. Now, why is that important? Well, it has a lot of implications on testing of code, right? Because if you look here, the cyclomatic complexity is essentially giving an upper bound on the branch coverage. So how many test cases do you need to have visited every branch within your code? And also a lower bound on path coverage, right? Because due to loops, there can be many more paths than you have branch instructions, right? So this is one that is very old, 1976. So it comes, essentially out of the first software crisis, where people realized that software is becoming more of a manufacturing process, and therefore we have to apply professional standards to the creation and maintenance of code. Another traditional metric, very controversial, is the line of code. Right? And shortly after the cyclomatic complexity was first published, people were starting to kind of measure how much this is a predictor, for instance, for faults in software. And some, at least, claimed that it was a good predictor, but primarily because complexity is very often highly correlated with the total number of lines of code. And since calculating complexity is much more involved than calculating or counting the number of lines of code, they essentially proposed, let's do the simple thing. It's a good approximation, right? So that sounds reasonable. More lines of code, especially in traditional procedure programming, typically correlate very well to the complexity of a piece of code, right? And it's also correlated to effort, and that's where we can nicely tie it into the more holistic metrics, right? So you can say, if a problem needs to be expressed in 10,000 lines of code, I know how many man hours, man month, or whatever I need to assign to a project, right? Now, the devil here is in the detail, because what is really a line of code, right? This is the problem where debates start. Is it, minus formatting? Do we have to clean white spaces? Do we also consider comments? Comments by themselves are almost a religious flame war on themselves, right? Because traditionally it was always encouraged to document every line of code and express what you're doing. And then people in software engineering came and said, if you have to do that, that's actually a code smell. It's a bad thing, right? Because if you have to explain your code, then the code is not expressive. So you're doing something wrong in the first place. But in fact, the percentage of comments by itself has been proposed as a metric for code quality, right? So there are definitely contradicting ideas of what code quality is and how we should measure them. Now, the reason why in modern languages these traditional metrics are very, very limited is that we came up with something that was called object-oriented programming, right? And if you think about it, OOP is really a game changer in terms of complexity, because we now have additional dimensions, various additional dimensions in how we can make our code more complex and less maintainable, right? And that is, for instance, through having deep inheritances, right? So these metrics do not work very well with OOP, and people started to think about how can we go beyond. How can we express the special complexity that comes through inheritance, or also the special complexity that comes through coupling, right? So if we just take a bit of a step back, right? If you want to propose a metric and you want to do it in a somewhat scientifically sound way, you start with a question, right? And the question here is, how can we predict, for instance, fault frequency as a metric through a code metric, right? And then you start with a couple of hypotheses. So you make some more or less estimated guesses as to what might be influential factors that can influence the outcome of this question. After you have that, you go to the experimentation or analysis phase. So you possibly look at a lot of different software products, compute your metrics that you propose, and then in the end, you can draw conclusions, right? Either you accept the hypothesis or you reject it, or you accept the null hypothesis to be more precise, right? Very often, this is also an iterative process, but in the end, it looks like that, right? You have your final hypothesis, and it's now nicely justified by experimental evidence. And this is what happened in '94 when Chidamber and Camera for the first time proposed a software quality metric or a set of software quality metrics that were specifically tailored for OOP, so addressing this gap that has started to become more and more pressing with regard to the old metrics, and also one that has actual theoretical underpinning, right? So rather than just guessing a number of things that might be contributors, they actually did a very thorough job of justifying, even using essential algebra, justifying why those factors contribute to code complexity and other problems. So their set of hypotheses were, it is a function of, the number of member functions in a class. It is correlated with your position of a class within the inheritance lattice. Well, you can substitute tree if you're a Java programmer, but you might have languages like C++ that allow multiple inheritance, and then it's not a tree anymore, right? It corresponds with something that they called the response set. That's a bit of an inheritance to, the small talk way of programming, where you're sending a message, and formally the execution of the method is a response to the message that you send to the class, right? It is also correlated with the number of children that a class might have. And then we have coupling, and we have low cohesion as additional factors, right? So those were the hypotheses, and they led to a metric suite that is very well known as the CK metric suite. And still, a lot of tools will give you some variation of the metrics that these two people define, right? So if you look a little bit more into the details, the first metric is called weighted methods per class, right? WMC. And WMC is essentially the sum of all the cyclomatic complexities of every method, okay? And therefore, if every method had a complexity of 1, it would be simply the number of methods per class. But essentially, it takes into account that in practice, in OOP programming, you can take one very complicated method and trivially break it down into multiple methods without reducing the overall complexity of what your program does, right? You can just factor out essentially every branch instruction into an own method, right? But it's kind of equivalent, having that versus everything in one big method. So, in some sense, this is the OOP version of cyclomatic complexity that is adjusting for the specific properties of classes and their role. The next method is, the next metric is the inheritance tree, depth of inheritance tree metric, right? So for every class, you essentially count the maximal path from an object to the root class. And again, the maximum here is primarily because they did that for C++ originally, right? Where you have multiple inheritance and therefore multiple competing classes, path potentially to the root class. So the intuition here is the deeper you are in an inheritance tree, the more chance you have for reuse, right? But also the more complex it becomes to predict the behavior of the class, because you have more things that are kind of, within the scope that you look at, they are secretly inherited from superclasses, right? There is more functionality that you cannot see right away, right? And then because of the deeper trees, you also have higher design complexity, and there is a tendency that more methods and classes are involved in overall defining the behavior of your class. The next metric is called number of children, right? So you simply count the number of immediate descendants. And again, this is a little bit, has to be instantiated for your specific programming language, what that means. In their original work, they just considered direct and, explicit inheritance. The intuition here is the higher the number of children is, the more reuse you have of functionality of the base class, right, in different contexts. And that is, again, potential for problems. And the greater the number of children is, the higher the likelihood that you have pushed improper abstractions into the base class just because it was convenient, right? So, another metric is coupling between objects, CBO. And here we simply count the number of other classes to which an object is coupled. Right? And coupling creates dependencies. Coupling also restricts the way in how you can evolve a class. So the intuition here is coupling essentially prevents reuse, right? And it can point to poor encapsulation. And in the end, high coupling typically leads to a high testing effort, because you have to consider multiple ways. For instance, if we are talking about a member variable, right, you have multiple ways in which the state can change if this is a public member. And that is a very high form of coupling. Now, the metric response for class, I already told you, think of it in the message passing small talk kind of way, right? So you look at a method and then essentially you build the transitive hull of all the other methods that are called in response to calling this method. Okay? Essentially, that's a very good metric of the internal complexity of a method. In practice, very often people find this to be too computationally intensive to determine for large code bases. So don't be surprised if people use this metric, but what they really do is just looking at the internal calls within the same class scope, right? Because this is something that you can essentially determine with a one-pass sweep over the code. So the intuition again here is the understandability and testability of the class degrades if you have an excessive transitive hull of other methods that are invoked from a method. Right, and then the final one, this is the classic lack of cohesion. So if you have a class in which all the methods are really poorly related to each other, evidence here is given by the fact that they touch almost no common variables, right? Then you have a low similarity in these methods. They are all doing something differently, and therefore, by theory, they should not even be in the same class, right? And if you still put them in a class, you increase the complexity, because by just looking at the name of the class, it's very difficult to figure out what a method does, because there are so many different methods that all do different things. That, again, is the intuition. Okay? Any questions so far? No? All right, so let's come to the effectiveness of quality metrics. Many of those metrics have been around for a long time, right? Especially those that I talked about. And indeed, people in the software engineering community have tried to measure empirically the impact of those metrics and to which extent they are predictors for code quality. Right? So one study, for instance, by Lee and others in 1993 looked at two Ada projects and essentially tried to see to which extent those different metrics are a good predictor for the number of changes per class, right? And that would be, if a class is how the long-term maintainability of a class is. Now, you see a problem here that will be recurring when I talk about the other studies. Two projects is not really a large empirical base, right? And also it's Ada, so, it's very difficult to relate that to modern programming techniques, right? But at least that was one of the studies that was highly regarded, and most of the things that I will cite here, have in the order of 1,000 citations, so they are really considered reference points for the rest of the community. If we talk about using those metrics as a predictor for fault detection, we have several studies that are all revolving around different projects. starting with the first one that looked into several C++ projects, and they calculated all these metrics for every project, and then statistically try to see, first of all, which of the metrics are good predictors, so have high significance with faults, right? And then also they did a principal component analysis and essentially tried to figure out if those are independent predictors or if they are dependent in any way, and therefore we can get rid of one or two. Right? Now here, at least we have several projects. Well, the source of those projects is all student code, if you read the paper carefully, right? So again, and it is C++. So, you know, both is kind of a threat to validity if we talk about, you know, modern programming techniques in general and also industry best practices. Right? If we look at the second one, they looked at a set of 405 C++ classes, 301 Java classes, so at least they have some Java in them. You know, in view of what we talked before, those numbers look impressive. If you look at any, you know, mundane Java library, then 301 Java classes is not a very high number at all. Again, I would call this a threat to validity. And when we go to the more deeper analysis of the metrics, they also were not conclusive in all of them, right? The third one here, you and others in 2002, looked at what they called a large network management system, right? So you need to smile. It's 34,000 lines of code. You know, I think that those were even in 2002 not necessarily a large project, but you know, that's academia. You can always claim 123 classes. You know, yeah. If we are honest about it, also not a very large empirical base. This one here from 2005, I think, is one of the best indicators and also one of the most thorough studies. They looked essentially at the entire Mozilla code base, so at least we have a real project here, a real product, and they retrieved all the bugs from Bugzilla, tried to boil them down and essentially blame individual points of code. Now, for a variety of reasons, when you do that, first of all, it's a very, very high amount of labor that you have to put into that, right? There is not a lot of good automation that you can do. The second thing is, it's not always immediately clear that you can blame a bug on a code location. So the actual number of bugs that were in Bugzilla at that time is you know, quite a bit larger. But in the end, at least they had roughly 9,000 they could use. So I would say in terms of overall evaluation, that's possibly the most thorough one and the most you know, comprehensive one. Well, with the exception that, again, it focuses on C++, so there might be some bias introduced by the language. So, if we look at the grand scoring board, you know, we have all the different metrics here. We have the studies that I presented on the last slide, and you see the result is somewhat mixed, right? We indeed have some metrics that score strong significance across essentially all of the studies. And that makes them, you know, good indicators, something that I would personally think can be used in practice very well. We also have a couple of lines here that have stark discrepancies in the sense that the same metric in one study has strong significance, but in another study has strong negative significance, which means it's a strong significant indicator for exactly the opposite. Right? And that means, you know, either there might be something wrong or different in the study, and that's always a possibility that there are some structural problems. Maybe the code is not representative. Basili, for instance, in their paper mentioned that they had to differentiate for user interface and non-user interface code. So the method complexity, the weighted method complexity, is in their study only a strong indicator for user interface code, right? But overall, you know, it is a little bit mixed. And my personal takeaway is it might be because of the poor, you know, empirical evidence in some of those studies, at least. All right, so this is the level of class-based software quality metrics. Any questions at this point? No? So if we talk about OSGi, modern Java programming, right? Class level is indeed not the only thing that matters, and you might even argue that it matters the least, right? If we look into package level metrics, then we necessarily come to the work of Robert Cecil Martin, who, among many other things in the space of agile software development, also defined a couple of very useful quality metrics that are operating on a packet level, right? And the entire idea here is we look at a packet and we try to determine the degree of coupling between packets, right? Coupling is bad for us because coupling means that those packages are very tightly integrated. They might access state of the other packet, and you can almost not test them in isolation. You can almost not reuse them, one or the other, without the other, right? So in his work, one of the metrics that he uses is efferent coupling, and that's essentially, if you look at a package, you look at a specific class, you determine the number of outgoing dependencies that you have to other packages, right? Very clearly, that's the outgoing angle. And when you do that, you can also do the opposite, which is the efferent coupling, and that's the incoming dependencies per class, right? And if we take those two, we can calculate a metric for instability out of them, right? So we take the external over the sum of the two forms of couplings. So this is essentially a ratio, right? What is the external coupling to the ratio of total coupling? And then we have a metric for instability that has values from 0 to 1, because it essentially corresponds to percentage, right? So now the empirical suggestion here, or the heuristics, is preferably you want either highly stable packages, and those can be identified by having an instability value between 0 and 0.3, or you want highly unstable packets. Both is fine, interestingly, right? What you don't want is something somewhere in the middle. And that's kind of interesting, right? But if you have highly stable packets, that means that they have very well-defined external dependencies. They are very strong in that, right? And sorry, no, that's the opposite. If you have highly unstable packets, then you have a lot of external dependencies. If you have highly stable packets, then this is very limited, right? But in both cases, you can reach a conclusion over how you want to use a packet, right? If you consider it to be stable or unstable. If you don't know, then you just cannot make anything out of it. That's the idea here. Okay, so let's revisit our model of scientific methodology and instantiate it for our question here, right? So the question is, which benefits does OSGi provide in terms of software quality? That's the question that we want to answer. We are now at the point where we have to essentially formulate our hypotheses, and then we can go to the experiment and the analysis, right? So the hypothesis here is we have a couple of metrics, and we have an intuition where OSGi can help, right? Just based on our experience. If we look at this group here, these metrics, right? So the weighted method complexity, we also have the depth of inheritance in inheritance tree, we have the number of children, and the lack of cohesion. Those are per class metrics that I honestly don't see how they are directly affected by OSGi, right? But if you remember our little diagram here, fortunately those are the ones that across those studies are not very good indicators anyway. Right? So, in the end, they might or might not be affected by OSGi, but probably more through secondary influences, that people who are coding in OSGi might do things to their code in spirit of, more rigidity or more thorough methodology or so. But from the way how OSGi works, I don't see any way how those metrics could be directly be influenced. If we look at the two here, and fortunately those are the ones that show very strong correlation across all of the different studies, we have the CBO, right? So the coupling between objects, and we have RFC, the response for a class. Both of them are, and that's my opinion, right? That's my hypothesis. Both of them are affected by OSGi. The coupling is definitely affected because in OSGi you cannot just arbitrarily, have dependencies between packages without at some point paying the price for it by having to declare it or having to tell your tool how to detect them, right? So package level dependencies are explicit. And if you have class level dependencies and they cross the package boundary, they have to become explicit, right? We also have this facility of services, which is a great way of doing decoupling in your system, right? You register a service under a service interface, and now the implementation is no longer a dependency to your consumer, only the service interfaces, right? So those are two ways in which I can easily see CBO being affected positively by the OSGi programming model. And RFC, services can potentially have a huge impact because now you're separating consumer from producer side, right, of a service. And thereby, because they are loosely coupled from the analysis point of view, you're cutting the dependency chain at this point. So you're no longer going into the entire implementation at every point where you use a service, right? At that point, it's just a call against the service interface. All right. If we look into the per packet metrics, then I think the picture is relatively clear, right? This is the point where OSGi is very, very different from standard Java. The packet coupling, I'm very sure, unless you're using things like require bundle, right, is dramatically lower. I would be very surprised to not find that, just based on the projects that I looked at and that I worked on. And then the interesting point here is if we are able to reduce both the efferent and the efferent coupling, what does it mean for the instability? Potentially, if we do it to the same degree, then the instability should not change, right? Because we are reducing both values the same way. All right. Another interesting angle, by the way, is here looking at the trajectory of change. I will possibly talk a little bit more about that in my next slide, but if we look into projects, I would be very interested to see at which point did they adopt OSGi and to which degree did they adopt OSGi, and how do the metrics change now in the evolution of the code, right? Because you might all know this from practice. Buying into the OSGi model is never a binary thing, right? You start with something simple, and then, the more you buy into this programming model, the more you're changing and modifying your code in such a way that maybe you make more use of services and lose coupling and go away from the tightly coupled way of standard Java. All right, so what is the plan of attack in order to empirically validate those hypotheses? Well, we want to research how OSGi's modularity and service model affects code quality metrics, right? For that, we have to look at, for instance, open source projects. Those are very great sources for empirical studies. I think it's fair to say before open source became a thing, empirical software engineering was really, really limited because nobody wanted to share their code, right? That's also a fair defense for those very old projects that had to resort to student code. Well, they couldn't go to GitHub and look into, I don't know how many million projects, possibly 50 million projects at this point, right? We have the ability, and we can do that, right? So we want to see how the metrics using or not using OSGi are correlated with defects. And fortunately, we also have public bug databases for many projects that we can tap into. Now, again, the problem is the manual labor in doing the correlations, but there are some tools in the community that can make this a little bit simpler. And then, to me, the most interesting question is, how does modularity support the evolution of software over time, right? And again, because these days we use source code repositories that keep a full history of a project, we have a great chance to actually look at these, code in motion, rather than the one-time snapshot kind of empirical analysis that has been done in this field so far. Okay, and then finally, if we are at that, maybe given that we have metrics at a class level, at a package level, we might also define new metrics for the general problem of modularity as in OSGi, because there might be effects that the current metrics do not quantify and predict successfully. All right, so with that said, I come quickly to my conclusion. So there are many different software quality metrics that can be used. You might be using some of them in your projects. OSGi, due to its structural constraints, has the potential to improve code quality. At least that's our hypothesis, right? And we are looking into empirically showing these benefits by looking into large open source projects. And of course, if you have a large project using or not using OSGi, and you would like to be part of the study, we are more than happy to work with you and extend our empirical base. And hopefully, stay tuned for results. Hopefully, next time, EclipseCon Europe, I will have a whole presentation just on the findings of this study. Thank you very much.